this point, we've only been able to describe gravity in terms of a kind of circular logic, Newton's second law definition, that is specific to cases where an object is near the surface of Earth. That happens to relate to most of our day-to-day observations. But we're also able to see celestial objects, like, for example, the moon from Earth. And our definition of weight does not work in that circumstance. Um, Instead, Newton, in developing all of these rules for mechanics, these force kinematics relationships, came up with a definition for a more unified definition of the force due to gravity. That is a force that is exerted between two objects that are separated by some distance. This was largely developed by observing how objects move around in the solar system, which is that they move in circular orbits around each other. And based on those observations and the three laws we've already talked about for Newtonian mechanics, a more robust catalog of forces style definition for the force of gravity was developed, where if you have two objects and they're separated by some distance, they will exert a force on each other if both objects have mass. So force of gravity is defined as a force of one mass attracting another mass. It's exclusively an attractive force. It's a third law force, just like all forces. So you need two objects to have the force. And if object one exerts a force on object two, then object two must exert the same force back on object one. And the way this is defined is there is a constant. So there's this gravitational constant. And the way this force works then is it's directly proportional to the mass of both objects. So mass of object one, mass of object two, divided by the distance between those objects squared. So that's the general idea of the force due to gravity that you can put into your catalog of forces. It works just like all the other catalog of forces, meaning there's certain physical qualities and quantities that we can get from a situation, i.e. the mass of two objects and the distance between them. And based on those inputs, we can then say some force must exist, it points this direction, and it is this big, which we could then throw into a free body diagram to describe the resultant kinematics of whatever the situation was, right? Because any net force equals ma, and this is one force that could go into several forces acting on an object that may or may not contribute to a net force. This definition of gravity, which tends to be called big G gravity, as opposed to weight, which comes from the little g circular definition on the surface of Earth, can be used to get three useful quantities. One, the acceleration due to gravity is not the same everywhere in the universe. It's 9.8 meters per second squared near the surface of Earth. It's different in different places, including objects in orbit around Earth. Depending on how far away they are, they experience different gravitational accelerations than we experience down here near the surface of the Earth. One of the most obvious ones is the moon. You can see the moon, it's close enough to see. It's not accelerating at 9.8 meters per second squared towards the center of Earth. Um, Orbital velocity is then something else you can get for satellites, i.e. the moon, or satellites in low Earth orbit, for example. You can calculate the speed with which they can orbit, or also the period of their orbits if they're orbiting at a constant circular velocity, circular speed. All right, so let's derive these three relationships based on this top one using Newton's laws. Okay, start with this one. That is too thick. I'm going to thin that down a little. There we go. So first, how can you use this new definition in Newton's laws to establish that that should be true? All right, well, let's say you're on the surface of some planet. Here's a zoomed out picture. You're there, planet's here. There's a distance between you. On a planet, things tend to have very different relative dimensions, meaning your height is basically insignificant relative to the radius of Earth, such that the distance that separates your center of mass, which is how we calculate these distances, to the center of Earth is effectively equal to the radius of the planet or whatever you're on. And we already know that, if there's no other forces acting on you, or even if there aren't, let's say there's not, so you're in free fall, that makes it easy. In that case, the force of gravity would be the net force. And in that case, you would be accelerating, right? F net equals ma. But in this case, if you're in free fall, very close to the surface of a planet, then F net would be Fg, because in your free body diagram, there would only be one force if you neglect drag. On the surface of the moon, this is easy. There's no gas, so there'd be no drag. And in that case, you would fall at m little g, and that'd be little g for whatever planet you're on. So force of gravity on whatever planet you're on, m times your gravitational acceleration on that planet. And that, by definition, would be your weight on that planet, right? So ma becomes that. Well, the force of gravity, we now have a definition for from over here. So if we were to set those two things equal, force of gravity, we now can define with some catalog type rules, is a constant times the mass of the planet times our mass, or whatever mass of object, over the distance between those two things. Well, if you're very close to the surface of the planet and you're small, that would just be the radius of the planet. That's what separates the center of you from the center of the planet, or the moon, or the whatever. That would then be equal to, well, that's this part. Well, Newton's second law still applies. It says if you have a net force acting on you, that's the left, then you must get a resultant ma. And in the case where your a is caused exclusively by the force of gravity, we call it little g, the acceleration due to gravity. So m little g of a planet. And this is, in this case, the mass of the object. I didn't put that subscript in, but this right here is the mass of the object, which then shows up on both sides. And what you find, and this is something we've already observed, is that the acceleration due to gravity on some planet will depend on the mass of the planet, which doesn't change for any object near the surface of the planet. The planet has its own mass, divided by the radius of the planet, which if the planet is a perfect sphere, then that would be the same at every point on the surface of the planet. And then that is simply equal to the gravitational acceleration experienced by any object on the surface of the planet, independent of its mass, which we've already kind of gone over when we talked about the kinematics of freefall. Gravitational acceleration doesn't depend on your mass. All right, so that's relationship one. Check. How about relationship two? In relationship two, we're saying we can learn something about orbits. Well, if you're in an orbit, let's say you have a planet and some satellite, could be like the moon, it will trace roughly a circular orbit. Your textbook talks about the fact that actually both objects technically move, but we're going to make the approximation that you tend to have a small object orbiting a big object. And for the purposes of these notes, we're going to assume that the big object is fixed in place and represents the center of the circle that is traced by the smaller object, such that there's then a fixed radius between the two objects and a fixed speed, such that this is a uniform circular motion when we have a small object orbiting around a big object. Well, in that case, we can talk about the satellite. So satellite, what's up with the satellite? Well, if we were to draw a free body diagram of what's up with the satellite, well, if this is like the moon orbiting Earth, for example, both objects exist in a vacuum. So there's no drag force. The objects aren't touching each other. So in our catalog of forces, we can't identify any contact forces, and we've only gotten to one magic long-range force, and that's the force of gravity. So the satellite, and I'll put it on the right, let's say when the satellite is here, then the radial line would point horizontally on the page. Then if we're the satellite, we would experience a force due to gravity from the planet we're orbiting. So this would be Fg applied to our satellite, right? And that's it. That's our entire free body diagram. So long as Fg is greater than 0, we necessarily have a net force. And more specifically, that net force could be called a centripetal force because it is the net force responsible for causing our uniform circular motion. Therefore, we can say that this Fg would be equal to the mass of our satellite times its centripetal acceleration, which could be described in terms of its constant circular speed squared, divided by the radius of the circle it's making, in which case that would be the radius of its orbit around the other object. That radius is just the distance between the center of the two objects, i.e. the distance from the center of the satellite to the center of the planet or moon or whatever it is that it's orbiting. All right, so that's the effect side. This is the effect side in Newton's second law. This is the cause side, but the cause side, again, we can express now with this catalog of force definitions in terms of other physical quantities, which would then become G times the mass of the planet or whatever it is that's being orbited times the mass of the satellite divided by the radius between those two things squared. And what we will again see is someone's mass ends up on both sides. Okay. Our orbit is R12. And so the mass of the satellite's on both sides, so it no longer matters. And let's see, what did I do here? Oh, this isn't squared. I should erase that. I'm sorry. Right? That's not how centripetal acceleration works. So there we go. That's what we would have. And if we then look, what we'd end up with is this r is in the denominator would cancel with the square. And we can solve for this. We can solve for velocity. If we did that, velocity is already by itself on the right. I'm going to redraw that on the right. I'm just going to say v orbit. So I've already dealt with the fact that it's squared by taking the square root of both sides, which means on the what used to be the left side, which is now becoming the right side, I'd have to put a square root of everything. And what do I have on the left down here at the bottom? Big G, mass of a planet, and the orbital radius. So we've now used our catalog of forces definition of big G gravity to derive this equation for an orbital speed, and it does indeed match what we said it would be. That's 2. Now for the third one, once we have this definition of orbital speed, we can just take what we understand from our previous notes about angular kinematics and representing angular kinematics in terms of periods or frequencies for that matter. And we can derive this equation just based on the definition of a period and the relationship between angular velocity and circular speed. So starting with the top one, we already defined that your speed when you travel in a circle, if it's constant, is equal to whatever constant angular velocity is associated with that speed based on where you are, how big your circle is, multiplied by the radius of the circle you make. And we've also already said you can describe an angular velocity as the angular displacement in one revolution, which is 2 pi radians, divided by the amount of time it takes to complete that, which by definition is something we call a period. So if we were to rearrange things to solve for t here, first off, we can combine these by putting this there, and that would become this. And if we were to solve for period, we would get that period is just equal to 2 pi radians times whatever the radius of the circle you are making, divided by the constant speed you're traveling with around that circle. Well, v orbit, we already have a solution for, so we can take what v orbit's equal to, substitute it in there. We notice that v orbit is equal to the square root of that business, so what we could say is square both sides, and I can get rid of that square root if that makes things easier to work with. And I would get 4 is 2 squared, pi squared is pi squared, r squared is r squared over v orbit squared. And that just means where I put v orbit squared, I can get rid of the square root over here on the right. I just put everything that's there, meaning this would be 4 pi squared r squared over, well, I have g, mass of the thing being orbited, we'll call it a planet. Then if I have something in the denominator of my denominator, which would be this r orbit, I can put it back into the numerator. So times r. If I simplify, I have r squared times r up top. I can combine those. I get 4 pi squared r cubed over big G times the mass of the planet. Now, big G is just a number with units. That's a constant. You'll get that at the top of your quizzes and your exams. That's basically just the proportionality factor that makes this thing work, meaning when you have this type of relationship, that's the number that makes things quantitatively work. If we then take the square root of both sides, because over here we say t orbit, not t squared, so square root both sides, and you get this underneath the square root, which is what we see there. Check.